Hello, challengers. We are here in this weekly live that happens every Tuesday at 10 p.m. London time. And for you who are here on Zoom, you can get the mind map at the end of this presentation. So congrats for you. We're here live, paying attention and focusing on your career. So today we're going to be talking about stack concepts. So why stack is important? So we use stacks for many things. We use stacks for recursion. We also use stacks for many algorithms. So it's an important data structure to be aware of because depending on the algorithm we get in a coding interview, the stack will be the best solution. And not using stack will require us to use a lot of code. And we don't want that. We want to create the code as simple as possible, right? So what are the main concepts of a stack? So the first important concept of a stack is that the way we put information and remove information on a stack is last in, first out. So it's like the real world. And I can actually show you on my book here. So as you can see here, there is so this is how it works, right? So last in, so basically we put the plate on the top. Can you see it? You can do like that if you can see it. Yes, perfect. So the last in, first out, how it works. So it's basically like the real world. So imagine a stack of plates. When you put information, it's like that, right? It's the first here, the second here, the third here. So it's last in, and the first out. So just imagine the real world scenario where we put the plate one on the top of the other, and then we remove the one that is on the top. So last in, first out, right? So this is an important concept. Okay. So as you could see, the last in, first out example is just like the real world. So we put one plate on the top of the other like a stack. So remember this example, then there's no mistake. You'll always remember how a stack works in programming because it works just like real world. So in a stack, there are some operations. The first one that we're going to explore is push. So when we push data to a stack, it's like pushing a plate to a stack, right? So you're going to put one on the top of the other. And the pop operation is going to remove the plate from the top, right? The push operation will add to the top until you create a stack of plates. And the pop operation will remove the plate that is on the top, right? So it's last in, first out, last in, first out, right? And the pick operation will only view the top element without removing it. View or get, whatever the name you prefer. And the isEmpty method will check if the stack is empty or not. So actually, the stack data structure is very simple. It's just like a stack in the real world. So, and what are the Java stack implementations? So there is the Java stack class, which is a legacy class and extends vector. And as you probably know, the vector class is actually thread safe. And in most cases, we don't need a thread safe stack. So that's why this class is not recommended to be used. So if you go to the documentation of ArrayDeque, for example, so what is an ArrayDeque? It's an array doubly linked list. So it's basically it's a queue that is double-ended, right? So basically you can use a queue or you can use a stack in the ArrayDeque. And if you go to the documentation of the ArrayDeque class, if you see the Java docs, it's going to say that the stack class is actually not recommended to be used, and it's actually preferred to use ArrayDeque because it's more performant And for most operations, it's going to be a lot better. So let's see here. There's actually lots of details on this stack. So let's explore some of them. Yeah, so the methods are pretty much the same. Push, pop, pick, empty, search. Like I said, stack is a legacy class. It extends vector. It's synchronized. And for most operations, it wouldn't need a synchronized class, right? So it's an overhead. It costs performance, and it's an inconsistent API as well. Because, for example, since the vector class has this method here, add index an element, so basically the stack class will extend this method from vector, right? And this violates the last in, first out principle of a stack. So that's another good reason to not use the stack class, right? And better alternatives, like I said, it's the ArrayDeque. So the ArrayDeque provides LIFO operations, last in, first out. Doesn't include methods that would break the stack contract, and even allows us to add synchronization when we need it. So we can use this method here, synchronize DQ, which is very interesting. And like I said, if you see the documentation from the ArrayDeque, it's gonna recommend to use ArrayDeque instead of a stack. So those are important points about it. And in the ArrayDeque, like I said, we have the same methods. It's more efficient. Yeah, it's preferred over the stack class, like I said. There is also the deque interface. Like I said, the deque interface is used for double-ended queues, which means that it can be used as a queue, and it can be used also as a stack. And if we want to work with a deque that is thread safe, we can use the concurrent linked deque. Okay, so like I said, it's a thread safe implementation. We also have the linked list, and the linked list can be used as a stack as well. And it has the methods add first, remove first, and get first, which is basically all we need. The time complexity of a stack is almost all of them O1. To push an element, it's O1. To pop an element, it's O1 as well. Then we have the pick method, O1. To search a value in the stack, it's ON because it would have to iterate the whole stack. Size check is O1, and isEmpty is O1. And what are the common applications of a stack? So one very common use for a stack is function call management. So we're going to see that very clearly when we debug a recursion method here. You're going to see that the methods will get stacked, right? And we also use for algorithms such as expression evaluation. And we're going to take a look at this algorithm. Obviously, it's not possible to go into all the details from those algorithms because of our time, but we're going to take a look at them. To undo mechanisms, so the famous undo operation from many operation systems, it's made with a stack. A stack has many useful things we can do. So we can also use the stack for the parentheses bracket matching algorithm to backtrack algorithms. We can also use it for browser history, which it makes sense because the latest websites you visit, it's going to be there, right? It's going to be stacked up. Syntax parsing and lots of other things we can use stack. And what are the common stack algorithms? So we're going to take a look at this one, reverse Polish notation evaluation, daily temperatures, next greater element, valid parentheses checking, infix to postfix conversion, that first search, and this algorithm is used for graphs, histogram, largest rectangle. And what are the limitations of a stack? So with a stack, we don't have random access to elements like we have with array. So with an array, to access an element by the index, it's a lot faster. So we get O1 to access any element, whereas we don't have access by index to a stack or to a queue. We don't have that. But the thing is that obviously we're going to be using stack for the problems that make sense to use it. So obviously it's not in all the problems that we can use stack. So that's pretty much it about the main concepts of a stack. As you can see, it's not that complicated. It's actually simple, the concepts of a stack. Now let's check some algorithms and some code that we can use stack. So firstly, let's check here what is the time complexity of a stack in code, because in code it's a lot clearer, right? So let's see here the stack class, for example, and just out of curiosity, let's explore how a stack works on the Java docs. So as you can see in the Java docs, they recommend here to use a DQ. So they say here, a more complete and consistent set of LIFO stack operations is provided by the DQ interface and its implementations. As you can see in the Java doc, they are recommended to use DQ with ArrayDeque. And as you can see here, the stack class extends a vector. Therefore, we get operations from the vector class that shouldn't be in the stack class. And it also makes the stack class synchronized, which is not that good. As you can see, it's synchronized, it's all synchronized, and you wouldn't need to synchronize all those elements, all those methods, right? So therefore, it's more efficient to use DQ for most situations. So let's go back. Okay, so as you can see, most of the operations are O1, right? Only to search an element, it would be ON, because you would have to iterate all the elements in the stack. And the size method, it's O1. The pop method is also O1, because basically we are just assessing the element on the top of the queue and we are removing it. So it's O1, that's why it's O1. And the isEmpty method, it's O1 as well, because it's just, we just check if the stack has any element or not. And here is the ArrayDeque. And the interesting thing about the ArrayDeque is that behind the scenes, it's actually an array of objects. So if you see here, this element is actually an array of objects. But the thing is that the interface of the ArrayDeque behaves as a stack or as a queue. So that's the important thing. Like behind the scenes, it doesn't really matter too much, because anyway, we can't access those elements by index, for example, because we use encapsulation here, right? So we can only use the interface of this method. And when I say the interface, I basically mean the public methods. So we have, for example, the addLast method, have the addAll method, offer first. So there are many methods here that will follow the contract of a stack or a queue. Okay, so let's continue. And most of the operations, they're pretty much the same, right? So O1 as well. And for the linked list, so a linked list behind the scenes. So if you see here, it's double-ended queue, right? Which means that we can use it as a queue and as a stack. And the interesting thing about the linked list class is that we don't have an array behind the scenes. We instead have a chain of objects. So we have a chain of nodes, which means that if we add many elements to a linked list, it's going to be a linked list. It's going to be kind of objects linked to each other. So one node linked to each other, right? So basically, we're going to create lots of nodes, and those nodes will have a reference to all the others, basically. So there is no array behind the scenes here, which is interesting, right? It's just a chain of objects. And the linked list follows the contract of a DQ because we are implementing it here, right? So yeah, in this case, we are declaring the linked list as a DQ. In this case, we have only the contract of a DQ and the implementation of a linked list. Obviously, if we declare a linked list with the list interface, then the linked list will behave as a list, right? So, but anyway, this is just polymorphism. And so, okay. And most of the operations here are all the same. It's O1 almost all of them. So that's pretty much it in terms of time complexity. So let's check the algorithms we have available here. So this is the first algorithm. So let me explain to you how is this problem. So basically in this algorithm, we have to know how many days we have to wait until we get our warmer temperature. So for example, given this list of temperatures, so 73 to 74, we have to wait 1 day. And 74 to 75, we have to wait 1 day. And from 75 until 76, we have to wait 4 days. And then from 71 to 76, we have to wait 2 days, right? And so on. Basically, that's the logic. And in the last element here, like it doesn't get warmer, so it's 0. So from 76 onwards, it doesn't get warmer, so it will be 0. And from 73 onwards, it won't get warmer as well, so it's 0 as well. And by the way, I'm going to share this code with you later so that you can debug it, because I know that it might take a while until you fully master it. So it might take some time, like debugging it until you get used to it. And it's even more difficult to master this algorithm if you're not used to the stack data structure. So it might be a little bit tricky, but you know, if you debug it enough times, you're going to be used to it. But anyway, let's debug a little bit so that you can see here. The first thing we get the size of the array. Size of the array is 8. And then we instantiate this array with 8 elements. And in this case, we're using a stack. We shouldn't use a stack, but just to show that it's okay for an algorithm to use a stack, right? But in production, it wouldn't be a good idea. Okay, so let's continue. The first thing we check if the stack is not empty. So in this case, it's still empty. So it will fall here and we're gonna push the index of 0. So basically we're gonna track the elements one by one here. And then, okay, the temperatures, if we see here, the temperatures is the first element, right? It's actually the second element. So it's the second element, and we compare that. So if we see here, so the stack has the index of 0. So it's gonna compare with the previous element. So let's see. So basically 74 is greater than 73. So we get the previous index. And 1 minus 0 is 1. Yeah, so basically we are already creating the result. So basically it's just 1 day here. Let's continue. 1 day as well. Here we have 4 days. And that's it. 1 day, 4 days, 2 days, 1 day, 0, 0. I highly recommend you guys to debug this code afterwards, because like I said, we don't have much time here to show all the algorithms. And we are only on the first one. So let's continue. That's the famous depth first search algorithm. And this is a graph. So what is a graph data structure? So it's basically an array of data, like a collection of data, where we have a way to explicitly connect the elements. So basically, in this case, we can see here that we use an edge. So an edge is a way to connect elements in a graph. So an array itself, it's not a graph because there's no explicit way to connect the elements. So it's basically implicit in an array, because like when we create an array, it's continuous memory, right? So we create, for example, if we create an array of 12 elements, there's no explicit way that we are connecting those elements. But here in this graph, there is a way, because we are using an edge, right, to connect the elements of this graph. Anyway, today it's not our goal to talk about graphs, but just to give you a gist of graphs. So let's then, so this is the graph we created. So basically this graph, what is this graph? It's a map of integer and a list of integer, right? So let's check here how that works. So we are instantiating this depth first search class, and then we add an edge in this graph. And when we add an edge, so we are basically just adding information to this list, right? So, and in this algorithm, we're gonna traverse this graph. So let's see here. And I'm gonna show you here the stack here on the methods. So we're gonna invoke this DFS helper. As you can see, the methods are being stacked here. This is the stack in the structure. So we have the other method being stacked, and then we visit all of those elements. And as we invoke those methods with recursion, they basically pop out from the stack. Okay, let's go to the next algorithm. This is the evaluate postfix operations. So what is the logic of this algorithm? So basically, we have an input, which could be in this example, like 21 and plus. So basically, we're gonna get this kind of operation in this kind of weird way, right? So basically, we have the number first, and then the operation to do the math. And here's the same, 3, then the operation to do the math. So in this case, we need to create this expression by basically putting the numbers and calculating them. So basically, that's what we're gonna do. And in this case, it's a lot more complicated. So basically, that's the logic, right? So number first, and like in this case, we're gonna divide 13 by 5. And then with the result of 13 divided by 5, we're gonna sum 4 with the result, right? So let's see how that code works then. Again, we are creating a stack, and it's this simple example here. Is the 2, 3 plus 5 multiplication, right? So, and here we use the famous char@, method. So we're gonna get the character from the string, because string behind the scene is actually an array, right? So we can access each letter, each character from the string using this method. And we check if this character is a digit. If it is a digit, so a character, the number 2 in a character is actually 50 in the ASCII table. And how can we convert that to int? We can simply do -0 as a character. Then we get the number. So we get, instead of the number 50, we get 2. So we are converting this character, this char, to integer. And then we keep on pushing the numbers. So we check if it's a digit, then we push the number. And so far, in this stack, we have 2 and 3, right? And it's not a digit, so it's gonna go here. And then we get the 2 numbers, which is 2. Well, because it's a stack, obviously it's gonna remove the last element, right? So last in, first out. So, and here we're gonna get the element 2. And then we use the new switch case operation from Java because it's nicer. And then we basically sum those 2 numbers. That's it. We have the first result, which is 5. And let's see how is the stack now. So we have the number 5 now, and let's continue. And if this character is a number, let's continue. Same logic, we're gonna get the last number, right? So it's gonna be 5 and 5. And now it's multiplication. So we're gonna multiply, and that's it. We get the result, 25. Let's continue. So this is a bit simpler. So in this problem, we need to find the next greater element for every element. So let's see some examples here. And if a greater element on the right doesn't exist, then we just insert a -1 in the array, okay? So we return an array here. So let's see. So basically in this one, 5 is a greater number. And here in this case, it's 25. So let's see how that works in practice. Let's debug it. On this one, I want to choose DQ. And you're gonna see that it's the same. It's gonna work like the stack class. Obviously, it's more performant than the stack class. And basically here, we're gonna initiate all the elements from this array, from this result array with -1. This method is very nice because basically that's what we're gonna do. We're gonna fill this result array with -1. So as you can see, it's -1, -1, -1, -1 and -1. So in here, we are processing all the elements from left to right. So let's continue here. So as you can notice, this is the same pattern from the daily temperature algorithm, right? So where is it? Yeah, it's the same pattern. And this is very important when we are doing coding interviews, because, you know, the more we get exposed to those problems with different data structures, it gets a lot easier to pass on those interviews. It's a problem when we don't get exposed to those algorithms, and then we get an algorithm that we never solve in our lives. We have no idea how to solve it. Then it gets very difficult. And actually, it's impossible to solve an algorithm if you don't have knowledge of data structures. So, like, even if you don't know the algorithm, it's okay. But if you know at least all data structures that you could use, and most algorithm strategies to solve the problems in a code interview, then your chances to pass will be a lot higher, right? So let's continue. So as you can see here, the next greater element is 5, right? And here we are just pushing the indexes, exactly the same pattern from the daily temperature algorithm. And then we use the pick method to, you know, get the previous elements, right? So let's check. And here we have the element of 25. There we go. We have 5, 25, 25, -1. So it makes sense because the next greater element here is 5. From here, it's 25. So we put 25 here. From here, it's also 25. But from 25 onwards, it's -1 because there's no greater element on the right. So that's pretty much it on this algorithm. Let's see the last algorithm. Let's see what time is it. Okay. And there is this valid parentheses algorithms as well. So the logic is that, so we have to make sure that we are opening and closing the parentheses. So in this case, it's true. In this other case, it's true, false, false, and true. Why it's false? Because we're not closing all the parentheses here. So let's debug this algorithm and see how it works then. Okay, so we're instantiating the stack class. Again, this method, we're going to be using this in many coding interviews to char array, right? So we transform our string to a char array, and then we check if this char is actually a parenthesis. And it is, right? We are opening parentheses here, and then we push this parenthesis here, and we continue to check if we are opening any kind of parentheses or brackets or whatever. And then if we are not opening parentheses, so in this case, we are closing parentheses, right? So then we invoke this method, is matching per. So we have the open, right? So the stack, we already have here the opening parentheses, and we check here if they match. If they don't match, we return false right away, because then it's a proof that we are closing the wrong one. So this one is going to return true as well. This one false because it won't match, so it's false. So this one, as you can see, it opens and closes, right? Both here, the parentheses and the square bracket, they close, but they are not in the right order. So therefore, it's false. But in this case here, they are in the right order. So yeah, it makes sense. So let's check. So this one will be true. Yeah, and it's true. So this if will be true twice. And when it's closing, it's going to get the latest string. In this case, it will be the bracket. And then that's why it's going to be true. So if we debug only the last one, let's debug this one because it is interesting. We can see clearly the use of a stack on this one. So we're going to stack up basically the bracket and the square bracket. We're going to push the bracket here and the square bracket because we're opening them twice. And then we're not opening anything right now. We are closing it, right? So here in the is matching pair, we pop the last element. In that case, it's the square bracket, right? So let's continue. And then that's pretty much it. After we test the square bracket, we test the bracket, and it returns true. So again, I will push this code to GitHub, and then you can debug all of these algorithms. That will definitely help you to be better prepared for coding interviews. And that's pretty much it, everyone. Let me just share again the mind map. Just a moment. Yeah, that's it. Any questions? If you have any questions, you can send on the chat. Yeah, definitely, Scott, because DQ. So Scott basically is asking here if we should use DQ instead of stack most of the time. And the answer is yes, because if you see here on the DQ documentation, actually it's not here, it's on the ArrayDeque. Let me go there. So if you go to ArrayDeque, actually they mentioned that on the stack class, right? It's not here. Let me see. Oh, actually, yeah, they say here. Yeah, so it says here that in the ArrayDeque class, that it's a resizable array implementation of the DQ interface. ArrayDeques have no capacity restrictions. They grow as necessary to support usage. They are not thread safe. In absence of external synchronization, they do not support concurrent access by multiple threads. No elements are prohibited. This class is likely to be faster than stack when used as a stack, and faster than linked list as used as a queue. So most ArrayDeque operations run in amortized constant time. So for most operations using an ArrayDeque or the DQ interface will be faster than stack. So why is that? Because if you check the stack class, so let's go back here, time complex, yeah, it's here. But if you check the stack class, there isn't much here. So it basically extends vector. And the thing is that vector is a synchronized collection. So everything here is pretty much synchronized, right? And the stack class also has methods that are synchronized. And most of the time, we don't need to use thread safe operations in a stack. So we don't need that most of the time. So this is like one reason why using an ArrayDeque will be more performant than using a stack. Because if you see, it's actually a legacy class. Like they know they made kind of a mistake here with this stack class. They say here, right? A more complete and consistent set of LIFO stack operations is provided by the DQ interface and its implementations, which should be used in preference to this class, for example. So basically it reuses the operations from the vector. So if you see here, the add element is from the vector class. So it's basically just reusing whatever they have on the vector class. So they are reusing them, but they have kind of the contract of a stack. But the thing is that because they are using inheritance, they inherit all of the vector methods. So it breaks the contract of a stack. It breaks the contract of a LIFO, right? So this class to be avoided, actually. I just used stack just for, didactic reasons, just to show you that if we want, we can use a stack, but actually it's not recommended. We should avoid it. Yeah, it's not good. Any other question? Great. Thank you so much, Scott. Thank you so much, everyone. I'll see you next week then, hopefully. Thank you so much, everyone. See you. Cheers.